Good morning, buongiorno, everyone. My name is Arnt. I have been with Bruker now since about 30 years. You may know me as the cooperator of Alan Coelho. So the two of us, we are behind the Topaz software, also working on it since about 30 years. And for a couple of years, I was focusing on quantitative phase analysis, and I had the great privilege to work with people like Ian Madsen and Nikki Scarlett, who I think are really icons in this area. I learned a lot, and I hope I can also give you some ideas of what they taught me today. So there's no way that I could give you a comprehensive overview over quantitative phase analysis in 1 hour. Absolutely not. In particular, not if we are looking at issues, requirements, problems. Why are there so many methods? Actually, I want to give you a very brief overview and focus on a couple of topics which I personally find interesting and which often enough present some traps for the unwary. So essentially, my presentation is a selection of a couple of slides which are found in the first 4 files here, which you can see on the screen, the PowerPoints. I'm going to share them all with you, so you will be able to download them later. So everything I'm going to talk about is found there in much more detail. I have also added 4 papers. They are public access, so that should not be a problem. They're called QPARR. That is the round robin for quantitative phase analysis, conducted in 2001 and 2002. Very important reading. Same for the RRRR, the Rietveld Refinement Round Robin. Very important reading. In my very personal opinion, you should not even attempt to do a single Rietveld refinement or quantitative analysis job as a beginner before reading these papers. They are so I would say educational. If you take your time, if you download the data, and if you understand the outcomes of the round robins, you will do a much better stop already from the start. So that is a strong recommendation. In the afternoon, late morning, there's a plan to do a quick walkthrough to Topaz. Again, there's no chance that we could do this in detail. However, there's also a tutorial on the list. This is essentially the step-by-step procedures I'm trying to go through later. We will see how far I can get. You all have the Topaz software also. It's a demo version, which is good until end of the year. And in the tutorial directory, you will also find all the files as an example for the round robins. So you can go home and work through them step by step and see how good you perform. So with that, let me start with a quick introduction into quantitative phase analysis. Now, quantitative phase analysis is obviously a method which you can apply once you identified all your phases. So the saying is, before you can quantify, you have to identify. And we learned a lot about that yesterday. It is the only truly phase-sensitive analytical method we have, and that's why it's so important. The mathematical basis of quantitative phase analysis is actually a solved problem. We mostly have to deal with limitations which are due either to sample properties, all sorts of sample properties. We heard about a lot of them yesterday, and I will also repeat some. But mostly actually the operator. We sometimes call it the picnic problem, P-I-C-N-I-C, problem in chair, not in computer. So again, I refer you to the round robin outcomes. It should be very helpful. So quantitative phase analysis, all but new. Already in 1919, people started to do quantitative phase analysis. Formalized first time by Klug and Alexander, very important guys who wrote kind of the Bible of XRD in the 40s and 50s. And what they are showing us already in these days is that the intensity of a peak is kind of proportional to the volume fraction of the face divided by the absorption coefficient. There's a constant involved. I don't want to go into the details here. You will find the mathematics in the PowerPoints I'm going to distribute. But the proportionality between intensity and here still volume fraction, we, however, do weight percent these days, is known since a long time. Now, single peak methods, as I said, known since many years, but severely limited in the application simply because of the peak overlap problem. The Rietveld method changed the situation drastically. Now, the original Rietveld implementation did not do quantitative phasor analysis. This was introduced years later. I find it interesting to refer you or to mention these three papers here by Bish and Howard, by Connor and Raven, and by Hill and Howard. That's a different Howard. Typically, in the context of quantitative phasor analysis, it is the third paper which is being referenced because it has been published, in 1987, the other two papers in 1988. But if you look at the receiving dates, Hill and Howard were the last by 3 days. Yeah. So all these 3 papers have been received within 3 days, and the one which is actually referred to in literature the most was the last of them by 3 days. So take-home message: if you have something to publish, don't wait. Very important. So what is important about the Rietveld method? Highly tolerant of peak overlap. It opens you a huge range of applications which you cannot do with single peak fitting, or with single peak methods, I should say. It is standardless. That is also very important. However, it has an issue, and we will come to that later. The Rietveld method, at least the traditional Rietveld method, can only produce relative phase content. This is important to keep in mind. It comes clear if you think about amorphous content, or if you think about phases which you cannot identify or which you simply missed. So in this case, you always have to be aware, by default, using the traditional Rietveld method, you only obtain relative phase abundance. Just two quick examples concerning the level of complexity you can deal with. This here is a cement. It has a large amount of amorphous phase, which is indicated here by this intensity distribution in blue. Clinker and cement, it is actually a solved problem. It is considered routine today. No way to do anything with single peak methods, obviously, because of the peak overlap. And there are additional issues. I mean, look at the background function. We will discuss that more in detail later. So 10 phases and more is not uncommon. There's often issues in such kind of samples because the different components, the different minerals here, have a different hardness. And if you grind such a sample, what happens easily is that you destroy the softer phases. There's polymorphism for some of the polymorphs in cement. There's even no accurate structure data existing yet. You have very chemical composition. So this is always an issue if you keep in mind that the Rietveld method requires crystal structures for each phase. Where do you get the crystal structures from? In case of doubt, from a database. But that is not necessarily representative to the structure you have in your sample. So a very important issue to keep in mind. Preferred orientation, yeah, we heard about that yesterday. Amorphous content. Still, clinker and cement is certainly routine these days. A different example, for example, here, a mineral sample from a quarry or a mine, I don't remember, 15 plus phases, absolutely not uncommon in such industries. Here, the different hardness is a big issue. Remember, the destroying of soft phases, like here, quartz, next to, let's say, a clay. So the sample preparation becomes a huge issue here. Where composition, the same thing, micro absorption, a particular problem, not so much in cement, but in general. This is actually a contribution on error I want to focus a lot on later. Stacking disorder, sometimes turbostratic. So with the traditional read-field method, it's all but easy. It is never a straightforward exercise. Let me continue with some requirements and limitations. Very selected, but I think very important too. So if we're looking at requirements, first of all, we need an ideal powder. We discussed the question what a powder is already yesterday, and I would say a few additional words to that. Sample preparation and presentation. So presenting the sample to the beam of the instrument, considering instrument geometry, for example. Should I use reflection? Should I use transmission? Is an important aspect. And appropriate data collection. I mean, what step size are you using? Typical question in the university in earlier days. Yeah, 0.02 degrees to theta. Why? Yeah, because my supervisor told me so. Not uncommon still today. So step size, counting time, to theta range to be collected. In my university, in the earlier days, where we still had scintillation counters and where measurement took 1 hour, the 2 theta range had to fit into a 1 hour slot. It didn't matter if the data quality was poor or not, because after 1 hour, the next student wanted to measure that up. So you should know which step time you use and why, and also for the step size. There's a couple of limitations I would like to highlight. Peak overlap and background, particle statistics, preferred orientation we discussed yesterday, and microabsorption. And I forgot to mention all the topics which are highlighted here in yellow I want to focus on. So this is the selective overview I want to give. There are also user errors, incomplete or wrong phase analysis, of course, incorrect crystal structures, space groups, atomic positions, occupancy factors. It happens more often than many people believe, and also thermal parameters, or Debye-Waller factors, as they are also called. I prefer thermal parameters. A particular issue which I would like to highlight today, inappropriate modeling of observed intensities. So, misfit in general is always an issue. Refinement of parameters which are not supported by the data, like occupancy factors. The most important limitations, more in detail in the presentation which I'm going to distribute to you, and I will now highlight the yellow topics. So, let me start with the question, what is a powder? It's a wonderful exam question, actually. What you often find in textbooks is a definition which reads a solid containing small crystallites or particles that will flow when agitated. This is a very arbitrary and a very limited definition, and it has nothing to do with what we're actually dealing with. If you look at the little icons on the website, you see the range of powders we are dealing with, and this is really from powders in common language up to bricks, if you want so. So if you go into the European norm 1330, what you find here is the currently official definition of what a powder is, and in particular what an ideal powder is. So one or more crystallites or particles or grains, they may crystalline or non-crystalline, this is important, which may form aggregates or agglomerates, and thus can be a loose powder in the sense of common language, a solid block, a thin film, or even a liquid. So even a brick or a liquid is a powder, according to the European norm. And if you think about it, it makes a lot of sense. This is the kind of samples we're dealing with anyway. An ideal powder, however, is what XRD needs. We need ideal powders And they are represented by a virtually unlimited number of sufficiently sized, randomly oriented, and, that's the worst part of it, spherical crystallites. So in essence, we're never dealing with an ideal powder. We should, because the entire theory of powder diffraction is based on the assumption of an ideal powder. And we need to keep this in mind as soon as we deviate from this requirement. We introduce issues, like particle size problems, preferred orientation, you name it. And we have to think about what to do with it. They will always reduce our accuracy. It depends on the level of accuracy you need, but it is important to keep that in mind. So one of my favorites is the so-called spottiness effect. It has also been discussed yesterday. If you are deviating from an ideal powder, you have issues like only a diffraction of a too small number of crystallites, which will give you a 2D intensity distribution like this one here. Or you have preferred orientation maybe, which gives an intensity distribution shown here. In any case, requiring corrections. The problem with these small number of particles, however, is it's entirely random. There is no correction available for that. If you encounter this problem, you are essentially done with your analysis. You either have to re-prepare your sample or you have to find a better sample. This is one of the most important limitations, and you wouldn't believe how often we see such powders and such data in the application lab in my company. It is one of the most frequent problems can see in user data. So diffraction of a single crystal, remember the definition also clearly said one or more crystallites. If it's one, it is clearly a single crystal. It's not suitable for powder diffraction normally. Of course, you could integrate over the rings, but why would you do that? I don't know. Do you know actually how powder diffractionists deal with single crystals? We grind them up. In a powder pattern, you will observe the deviations like here, and I have a larger picture here. So this is a mixture of corundum, magnetite, zircon. The concentration is well known. This is one of the samples from the quantitative phase analysis round robins, which I mentioned. You will get the paper. And, at first glance, also if you look at the difference curve, it looks like preferred orientation, but it is not. If you think about the origin of preferred orientation, and if you think about crystal size, then it becomes obvious the larger your crystallites are, the more likely also preferred orientation becomes. And a single crystal is actually the most extreme case of preferred orientation you could think of. But the important point is, if you have spottiness effects, and they are not so easily to be recognized just from a misfit, then you are done. If you are lucky and you have someone in your lab with a 2D detector, what you would observe is, for example, a pattern like here, that you have nice rings and other rings which are actually more spots than rings. In this moment, if you see such a 2D image of your sample, reconsider, restart, go back to zero. Now, there is still some hope for you who operate standard powder diffractometers with point or with linear detectors. If you have a sample with a spottiness problem, it will show up also in your powder patterns. It is always characterized by such saggy peaks. This is not to be confused with counting statistics. You can see that the counting statistics is small. So this is not just counting statistics, and it cannot be, because if that was counting statistics, then the peaks of corundum should be affected equally. So what you want to do is you take your sample, you do a measurement, you do not rotate. You do your measurement, then you do the next measurement after turning the sample a few 10 degrees. Next measurement, turn the sample a few 10 degrees, next measurement. And then you can see these sort of intensity variations and sagginess. that tells you I have a particle size problem. Peak overlap and background. I have to say this is really a playground which I personally like a lot. We will do actually an exam later. I don't think I have time within this session, but we will do it later this morning if needed. Would you say you can tell me what the peak intensities are, what the amorphous band intensity is, because there is obviously some amorphous material, and what the background is? So what we typically do is as crude as the Pauli fractionists with the single crystals. No? We just subtract the background and ignore it, right? It is a point which is also becoming important for you, I believe, tomorrow. I do not know what Max is going to show in detail, but the subtraction or the determination of not simply background, but the capillary in your data, if you do PDF analysis, has the same background when it comes to determining between the capillary intensity and the actual sample intensity. So what I'm going to show you later today is a methodology which you can also use in the context of PDF analysis. So here in this particular case, I had the luxury of a pure amorphous sample, because this here is a mixture, an artificial mixture with known weights. If I know the amorphous content intensity distribution, then I can use it as a refinement model. I can determine this intensity distribution, for example, with a series of single peaks, or maybe with a fake Pauli refinement. I show this later. Fix the intensities and scale them up and down in the refinement. So as a model for my amorphous content. The same thing for the instrument background. So I can also determine the instrument background with a sufficient standard. And if your instrument does not change, you can use this as a model for all your subsequent analysis. You will not use it as a hard constraint. You will typically add a linear background function on top of that and refine on these parameters a little bit. This allows you also to distort these models a little bit, but it can be done. It is a little bit more laborious, but if you're doing a type of analysis where the background is of importance because it has important data, then I think you will find this useful. So my all-time favorite of errors in quantitative phase analysis is called microabsorption. And my second best favorite is thermal parameters, ordered by Warner factors. Now the microabsorption error is the largest source of residual error in quantitative phase analysis. Residual means uncorrected and normally goes through undetected. It occurs if you have a sample where you have two or more phases with different absorption coefficients. Then you intrinsically run into this error, but it is not generally known. On top of that, you have an issue because of the different grain size and generally a size distribution between phases, which also cause microabsorption problems. So the microabsorption problem is consisting of two effects. First of all, different absorption coefficients of the different phases and different size distributions. I go into the details in a second. The second error, which often goes through undetected, is incorrect thermal parameters. So you go into your structure database and you know, for the quantitative phase analysis or your structural refinement, maybe you have your structure models, you have your coordinates, your space group, lattice parameters, and so on, and thermal parameters. But how would you know if these thermal parameters are correct? So many times you will find so drastically wrong thermal parameters, or even no thermal parameters at all. So what is your software doing then? Imagine you have structure data and there's no thermal parameters given, most software will then apply a default. They will set all missing temperature factors to 0, or to 1, or to 0.5. It depends on the software. Already, if you have a structure and you note, if you look at the structure data, that there is some thermal parameters like 0.5 or 0.7, exactly, then, this should raise an alarm. Why is that important? If you look at the impact of thermal parameters, you can see that this is a effect which drastically reduces intensities as a function of 2 theta, as you go to higher angles 2 theta. If this value is incorrect, you will have a very strong correlation with your scale factor. And if the scale factor is off, your quant is off. So let me talk about the microabsorption effect first. So for high absorbing materials, what you will find is that the beam will be absorbed more at the surface of your sample. Only a fraction of the grains will diffract, and the intensity of such phases with high absorption will be underestimated. So in general, the quant results of high absorbing phases will be underestimated, and for low absorbers, it's just the other way around. Consider the example CPD4 from the IUCR round robin. And again, you have all the information in the paper which I'm going to distribute. And consider the mass absorption coefficients here for the 3 phases: aluminum oxide, iron oxide, and zirconium silicate, for 3 different wavelengths: copper K alpha, cobalt K alpha, and moly K alpha. I'm comparing these because one of the rules of thumb is, if you believe you have a microabsorption problem, or if you know you have a microabsorption problem, change the wavelength. This can help sometimes, but as we can see here, not often. So in this particular case, you see here values like 48, 44, same order of magnitude, 117. This is more than a factor of 2. You will already see microabsorption effects. For copper, it is pretty dominant, pretty clear between corundum and iron oxide. And moly here, 0.1 versus 26. This is already a lot. More than 2 orders of magnitude. So changing the wavelength may sometimes help. The take-home message is, if you want to do quant, calculate the mass absorption coefficients and check if there are significant differences. If there are, then you have to be prepared, at least in mind, that you will have significant quantification errors. So if we are looking in this particular example here, and if you look at the fit of the data, it looks just perfect, right? 3 phases, who would guess that you are actually off by 6% absolute for corundum? 6%. This, if you think about it, this is a singular error. There's so many other errors which you have, or potential errors you have in your analysis. And only microabsorption contributes for not spectacular sample, if you think about it. 6% is really a lot. And I promise you, this is overseen by many every day. Maybe you don't need this accuracy. Maybe you're happy with semi-quant analysis as we've seen it yesterday, so that's fine. But at least please go home and know that there is such a massive error. And the worst part of it, it cannot be corrected. If you want to win a Nobel Prize, and I promise you the Nobel Prize, then solve the microabsorption problem. You will be famous like at least Rietveld. So it is an error which cannot be corrected. Any ideas what you could do to at least minimize it? That's something people normally do not want to hear, but we're automatically coming back to the good old traditional single peak methods. Yeah, we have to do calibration series. Now, for 2 or 3 phases, to do a calibration series is manageable from time to time. For a 10-phase sample, forget it. So changing the wavelengths often doesn't eliminate absorption contrast, but it may introduce other issues. Changing the wavelength, for example, can give you sample fluorescence. So this is something you want to keep in mind. Also, if you change the wavelength, you change the accessible Q range. No? So you compress and expand, thank you, your 2 theta scale. So all things you need to keep in mind if you decide to change the wavelength. And I mean, although it has become easy in today's laboratory diffractometers, comparatively easy to change a wavelength, it's still not fun. Changing the X-ray source is easy, but if you have optics to take care of as well, that's not an everyday's job. So there is a correction, however, which is proposed. It's called the Brindley correction. Unfortunately, and I apologize for that, you also find it in Topaz, but this is only because so many users put so much pressure on me and Ellen. The Brindley correction requires knowledge of the particle size for each phase. How do you get the particle size in your samples? It's not crystallite size, by the way. No? So some people do the mistake, they refine the crystallite size and use that in the Brindley correction. That is devastating. If you do that, it is only valid for spherical particles with uniform size. So already, if you look up the definition of the Brindley correction, if you look up the paper, it becomes clear that this is a correction which is in practice not usable. People use it anyway, and what they do is they overcorrect the data. Well, overcorrect is, I think, not the right term, but I want to be friendly. Don't use the Brindley correction ever. If you go home on Thursday and if you remember never to use the Brindley correction, then I have been successful today. Thermal parameters. They strongly correlate with the Rietveld scale factor. Many databases, as I told you, do not even include thermal parameters. So we can be all upset somehow. Is Tom here? Now the ICDD database is maybe a little bit pricey, but it is a curated database, and at least they do their best to try to find out even incorrect or obviously wrong thermal parameters, and they would not even or not easily accept any crystal structure where there are no thermal pieces at all. For other databases, this is not the case. Incorrect values of thermal parameters have significant impact on quantitative phase analysis. The weight percent errors will depend on the intensity distribution of your phase in the powder pattern. This is something I would like to show you quickly. If you have a problem with thermal parameters, for example, if you don't trust the values which you're using, refine them just for fun. Even if you can expect to refine meaningful thermal parameters from powder data most of the time, let alone in mixtures. But as soon as you see that your temperature factors start to change a lot, you have some sort of residual error in your data anyway. If that is correlated with your phase content, with the scale factors, then at least it is worthwhile to check the quality of the thermal parameters. I would not accept the refined parameters, just for fun. Just refine them just for fun. Do not save the results. Just see if your temperature factors change massively, and if in connection also the scale parameters change. It's a quality check if you want so. So this here is sample number 3 from the quantitative phase analysis round robin. Blue is the corundum. It has a pretty, well, of course, there's always an intensity drop towards high angles, but it's not a lot actually in corundum. But if you compare that with the fluoride, it becomes obvious what I want to tell you. No? So the impact of the intensity distribution here through thermal parameters is a different intensity distribution over 2 theta. And if you have phases where the intensity distribution is different, where you have a lot of high intensities, maybe for one phase at low angles to theta, and another phase has high intensities more at the high in the high angle region, then you know that you have a potential problem with thermal parameters. The zinc height behaves similar. So what does that mean in practice? This here is a plot which compares refinements, comparing the composition, the refined composition, with different temperature factor values going from 0 up to 1.5. 0, as I said, many software will use default values if the temperature factors are not given. Some software is actually giving 0. I think Topaz is giving 0.5, if I remember correctly. And this goes up to 1.5, the range of defaults which you can find. So here, this temperature factor for aluminum and oxygen, we're looking at corundum right now, is about 0.25, something like that. Now imagine you use different values for the temperature factor and have a look how the quantification goes astray. So this is massive. In the range of a temperature factor of 0.2 angstrom squared to 1 angstrom squared, you introduce 3% absolute error. Again, it depends on how accurate your refinements should be, but we have now 6% of residual error in microabsorption, another 3% for temperature factors. Sometimes errors cancel them out somehow, we know that, but I think this is very significant. This is important to know, and many people fall into this trap. So methodology, very quickly. I'm afraid I'm running out of time. We distinguish between single peak methods. Obviously, there is a couple. I'm not going to talk about them. And whole powder pattern methods. We have the traditional Rietveld method, which I would like to comment quickly. The internal-external standard method, the Ponks method, and I would like to say one or two words about artificial intelligence, because quantitative analysis has now also found its way in machine learning. So about the traditional Rietveld method, there's another classification which I should also mention, and that depends on the question if you want to consider amorphous content or not. So one class of methods allows you to quantify amorphous content via indirect measurement. So essentially you add a standard to your sample. This is something we normally never really want to do. Then you analyze the crystalline phases and you get the amorphous content by difference. Or by direct measurement in this case, and that is the case you normally want to prefer if you can, by modeling the amorphous content, which also gives you the chance to model more than one amorphous phase, because in the indirect measurement methods, you can only quantify the sum of all amorphous phases. Why is that important? Now, on the left side, you see a cement again with some amorphous phase, 25%. Now, this line here, this is the model used for the amorphous content here. So it assists the eye a little bit, but if you would look at this pattern without this intensity distribution here, would you say, hey, this is actually 25% amorphous phase? So amorphous content is overseen a lot, and therefore it is ignored, willingly or unwillingly. But even if you cannot see amorphous content by eye, it can have a substantial abundance in your sample. Maybe that's not important for you, but I find most of the time that people are shocked if you tell them, hey, you have 25 or even more % amorphous content, and they wouldn't know. And they have always reported relative phase amounts, but not absolute phase amounts. Here, just as a comparison, a different sample from a paper in 2011, just to illustrate that about the same amount of amorphous phase can be easily seen. So in this case, the direct measurement methods can help you whether you model the amorphous phase. You can also use the indirect method in this case. Here, if there is no visible intensity contribution, then there's also nothing to fit to. Therefore, in cases like here, you will need to do the indirect measurement in case of doubt with an internal standard. Otherwise, you will not be able to do the amorphous phase quantification. Now, the Rietveld analysis is very popular because it is a standardless method, and it is extremely convenient to use. And what happens is people use it indiscriminately. I would say 90–95% of all people doing quantitative phase analysis use the Rietveld method, although there may be many other methods which are much, much more suitable for the sample at hand. Now, the Rietveld method, always keep that in mind, the traditional Rietveld method assumes that all phases are crystalline and are included into the analysis. It has very limited modeling capabilities of amorphous content. I will show you an example in a second, but I would rather say, even though I show you a working example, you cannot use the traditional Rietveld method for quantification of amorphous content in general. Exceptions confirm the rule sometimes. Very important, again and again, it only produces relative phase amounts. Very important. It cannot correct for microabsorption effects, also important. No calibration, no microabsorption correction. As for the determination of amorphous content, so there is a tiny chance to model amorphous content in the Rietveld method if you know the crystal structure of your amorphous material and if you broaden your peaks extremely. This workaround would then allow you, for example, in this data set, to use a cristobalite structure to model silica flour. And by extreme broadening of your peaks in your pattern, you can approximate the intensity distribution of your amorphous content. But you will find it very hard in practice for the materials you are working on to find a crystal structure which is sufficiently suited to describe your amorphous content and to use it in the refinement just by broadening the peaks. So I would say this is an exception and never the rule. Clean. Internal standard method, here you spike the sample. People do not like to spike their samples. Why would you? You are contaminating your sample. It is a lot of efforts. If you have a lot of samples to spike, this is also not funny. However, it puts the results of the Rietveld method on an absolute base. So if you need absolute results, spiking is one way of doing it. And on top of that, no, not on top of that, in the opposite, although you are spiking your sample, although you have a additional sample of which you know the weight, you still cannot correct for microabsorption. So spiking and microabsorption, spiking is not a way to correct for microabsorption errors. And that is pretty sad, but it's a way as it is. So internal standard method is an indirect method for determination of amorphous content. Remember, the amorphous content which you cannot see by eye, where you cannot do a fit to obtain the amorphous content. Sample is contaminated. It gives you only the sum of all amorphous content. That's also important to remember. Cannot correct for microabsorption errors. By the way, if you add an internal standard, that's also something people tend to miss. They may add a microabsorption problem, by the way. Now, before you add a standard, first check the absorption coefficients. Does the mass absorption coefficient of your spike material fit to your sample? Or you add an additional microabsorption problem. The Pons method. This is Yeah, good. My big laugh. Sorry. The Pongs method entirely relies on the Rietveld method. However, the ZMV factor, where Z is the number of formula units in your unit cell, M is the mass of your unit cell, and V is the volume of your unit cell, which in the Rietveld method is of course obtained from your crystal structure, will be replaced by measured ZMV values. So you can quantify phases of which you do not know the crystal structure partially or at all. Think about disordered clays, think about any amorphous materials. I think I should save my time. We will do Pongs tomorrow. The Pongs method is usually the most accurate quantification method there is at this point of time, simply because you use observed intensities to describe the intensity distribution of your sample, while the Rietveld method is using calculated intensity distributions. So the Rietveld intensities, they rely, or they are only valid if your crystal structure is correct and representative to your sample. If that's not the case, then you of course introduce errors. With measured intensities, you get over that problem. It has the disadvantage that you have to do a one-time calibration. You have to do some spiking. Usually, you have to do this only once, at least only once for one wavelength. It will normally provide you with the most accurate results, because all the typical errors are structure related, are cancelled out in the Pongs method because you use observed intensity distributions. But as I said, we do this tomorrow. In the next session. So machine learning. There was a time when I got extremely attracted by artificial intelligence. I'm no longer. This is one of the reasons. What people do is, of course, they want to do quantitative phasor analysis, and artificial intelligence, as we all know from papers, can do everything better. The results are always better. They are faster, and the operators do no longer have to have any knowledge, because the artificial intelligence and the machine learning model does its job for you. It's not entirely the case, because what they need to do to train a machine learning model is they have to have some data. Now, if you're only dealing with some 5 to 10 to 15 phases out of the 1.1 million phases we know, you have to generate 10,000s, maybe 100,000s of powder patterns to train your machine learning model. It is entirely impossible to do this with observed data, of course. Maybe you can help though, however. Still, I mean, several 10,000 patterns for 5 to 10 phases in a particular system, that's quite a lot, and you cannot hope to do that. So what they are doing? They use calculated data, of course. They take crystal structures from databases. They calculate 10, 20,000 structures and more. Unfortunately, they have never heard about microabsorption effects. And also, unfortunately, you find many papers, and this here is one of them, Lee et al. In 2020. Many of the structures have no temperature factors at all. So they say deep learning technique for phase identification in multi-phase inorganic compounds using synthetic XRD powder patterns. From the terminology, often you can guess instantly that they are not Pauli diffractionists. We would never call that synthetic. Most importantly, what they do is they simulate mixtures by linear combination of singular patterns. Sure, that is of course what you would do. What else could you do? Microabsorption, you cannot correct it, so you also cannot predict it. But what happens then is they observe perfect face ID results for their faces here with very high classification numbers, so 99%, 98%, but a large discrepancy to quant results, and they wouldn't know why. But if you have a look at the samples they were using, they did QPA on mixtures in the lithium, aluminum, strontium oxide system that should ring an alarm bell instantly. So I contacted the authors, and they said, I mean, this is a citation. I share your concerns about the absorption depth problem, which I could not address in my work. So I'm not saying that these authors did not know about microabsorption effects. I cannot claim that, but I can claim they entirely did not consider it. So same authors found the solution to the problem. They used data again, and they evaluated them with Jesus. So the idea is, if we have problems with the classification in the machine learning model, we need to have some ground truth data from somewhere else. So we refine the data with Jesus, and we claim that the refined results from Jesus form the ground truth. And now what they observe is perfect agreement, as you would expect, because what happens is if you take data, you refine them in the software. The software cannot deal with the microabsorption. It gives you some results which are clearly off, how far off we have seen already. And now you do the machine learning, and you do the classification using your machine learning model, then you get, of course, exactly the same data, the same results as from Jesus. So the microabsorption error is one of the most troubling residual errors we have in quantitative phase analysis. And by the way, have a look at the samples here. Lithium, lanthanum, zirconium oxide. Here we have differences in the mass absorption coefficients for copper by a factor of up to 45. I told you, you can see microabsorption effects already by a difference by a factor of 2 or 3. So machine learning for quantitative phase analysis, I do not see it happen. Summary. These are the methods all the methods I could have been talking about today, no chance, but you have the detailed PowerPoints later on. If you're looking at your samples at home, and if you're wondering which method is the most suitable method for my samples, this table may help you. So this is a little comparison between the single peak method, Rietveld, internal standard method. I didn't talk about the external standard method. PONCS, LCM stands for linear calibration model. What you do is simply you determine a function, a linear function. In case of doubt, you form a calibration curve. And later on, you simply, for example, correct your Rietveld refined results with a calibration function. And degree of crystallinity. We can see here which of the methods are suitable for direct or indirect quantification of amorphous content. Rietveld method can do direct. The internal standard method can also do indirect. There are some requirements which may be important. Single peak quantitative phase analysis usually requires a calibration suit. You can also do I over I corundum, as we learned yesterday. But I over I corundum, the way how we've seen it, is a truly semi-quantitative method. With the calibration function, you will get extremely accurate. I mean, if you look at some work where people are quantifying polymorphs in pharmaceutical compounds, and if they do appropriate calibration suits, they get better than 0.1% absolute. So this is impressive. It can be done, but it cannot be generalized. Are there any methods which can deal with microabsorption? Yes, if you do a calibration. Always, if you do a calibration, you have a chance. The Pongs can also do it, but partially. So I would rather say no than yes, but to some extent. And then, of course, linear calibration method. Again, you are using a calibration function. You have mixtures with known weight, which you use to determine the calibration function. That can cancel out the microabsorption error. My summary: calibration methods usually have the potential to achieve the highest accuracy. Of course, you are calibrating out all potential errors ideally. Sample preparation and presentation microabsorption are the most important stumbling blocks in quantitative phasor analysis. Sample presentation and preparation is, I think, the worst. Preferred orientation can also lead to significant results, but at least there's some hope to correct it. Microabsorption is usually not. The traditional Rietveld method, this is what I said many times already, but I repeat it here because it's so important, because so many people are not aware of it, only deliver relative phase amounts. The Pongs method will usually deliver the most accurate results, because it includes a calibration step. Beware of the indiscriminate use of the Rietveld method. It is so easy to use, everybody uses it, but many people are not aware of the shortcomings of the Rietveld method. It's the usual comparison with your toolbox at home. You need to have more than one tool in your toolbox. And that is my final slide with a citation by the famous Arnt Kern. And nothing has changed. That is my take-home message in the past, 70 years. So we have the tools to become much more accurate. Often it is difficult, often it's not needed. But in essence, even though there are many examples where we can show that we can do quant with an accuracy of better than 1%, you will be in a range of several % absolute, 8%, not better.